Okay, thanks for that introduction. So today I want to start by considering these two images. On the left here, we have a map of extreme heat and cold days in the United States. And on the right, we have an estimate of population distribution estimated from nighttime lights. And what I want to talk about today is how to get from one to the other. That is, we do a pretty good job already of understanding these large-scale climate patterns. We can do an okay job of reconstructing them in the past, and we're getting increasingly better about forecasting how they might change in the future. The issue comes in trying to understand how these changes affect this. That is, how can we forecast potential social changes that are produced by changing large-scale climate patterns? And one of the big troubles that we have, the reasons why this is a difficult project, is because too often we think of human social systems as something like this, just as a distribution of dots on a map, when in reality, social systems are networks. So like an organism, a living organism, is really a network of nerves and veins. A society is really a network, an infrastructure network that allows for continuous flows of matter, information, and energy across space. So we can have hard infrastructure like this in the form of road systems. We can also think of canals. We can also think of less tangible pieces of infrastructure like our telecommunications network. And it's these continuous flows that actually make a society function. And so we have to understand how these work first before we can understand how a society might respond to large-scale climate changes. And so archaeology is actually really well placed to understand these long-term dynamics of infrastructure systems in the past and present. So not only do we work with hard human-made infrastructures, things like aqueducts, canals, or road systems, but we also work with things like luxury goods, ceramics, or other raw material sources that are the physical tracers of intangible networks of exchange and social interaction. And altogether, archaeology provides us this very long-term view on how these systems change over time. And what I want to focus on today is this idea of thinking of a social network as a form of infrastructure, just like a canal or a road system. So there's a couple of really important similarities that allows us to do this. The first is that we can think of all kinds of infrastructure as allowing for something to flow over space. Whether that's people, goods, information, that doesn't really matter. The idea is that there's some resource that we want, that we need to move from point A to point B, and infrastructure allows us to do that. Second is that infrastructure will inherently decay over time. It takes constant investments of time, energy, and effort in order to maintain it. So think about a canal system like here, the Hohokam Canal system. Every year you have to put many, many hours of labor into maintaining these canal systems so they can continue to allow for this resource flow that you want. And social networks act in much the same way. If you want to maintain a tight social relationship with someone, you have to actively invest in that relationship. You have to see them often. You have to interact frequently. And if you don't do that, if you don't actively invest in them, they'll decay over time. And the benefits, the information flows that you get from your social network will also degrade. And finally, this is the most important for us today, is that infrastructure networks will evolve so as to roughly balance the costs and the benefits of moving across space. So there's always a cost in moving across space that almost always correlates with distance, whether that's time or money or energy for moving across space. There's some cost in moving this thing that you want across space. And so the balance of how much you're able to maintain at infrastructure versus the decay rate is going to be a function of your benefits. So how much do you want this thing to continue providing a resource for you versus how quickly is it decaying and how difficult is it to work? So we can use this final principle to model patterns in complex networks by looking and systematizing the costs and benefits of interaction. And that can tell us something about their structure and function. So the question that I'm going to address today then is how do patterns of drought variability influence human social networks? And we're looking at this case study in the late pre-Hispanic period in the US Southwest. This is roughly the period from 1200 AD to 1450. And this is a period of large-scale social transformation and migration happening at around the same time as one of the most widespread, extensive droughts in the last 1,000 years. And it's been difficult over the past 100 years to exactly tie the drought event to this period of large-scale social transformation? Surely it influenced some way. These are all maize agriculturalists relying in large part, especially in the north, on rain-fed agriculture. So when the rain goes away, that's a big problem people have to deal with. But there's also pretty clear archaeological evidence that there's societal upheaval before the drought happened. And the response to the drought isn't instantaneous. It happens over several generations, this large-scale social transformation. And so we want to see on this large regional level, how can we relate these patterns that we see in these changes in the dots on the map, how can we relate them to these large-scale climate patterns and climate changes? So we'll be using this fantastic data set created in part by Barbara Mills and the Southwest Social Networks Project, part of this larger initiative called Cyber Southwest, which is bringing together all of the archaeological data in Arizona and New Mexico west of the Continental Divide. They've assembled a huge database, more than 1,000 well-dated sites from this region. They've organized them into different discrete 50-year time periods, and they've begun the really hard work of cataloging all of the ceramic and obsidian artifacts recovered from every single site. So the total database, the version that I used, was some 7.5 million ceramic artifacts. I'm sure it has grown vastly since then. There's nodding, I see. So this is an example of archaeological big data. So we're able to ask these kinds of questions of past social systems that we've never really been able to ask before. And this is because there's a lot of social and cultural information embedded in these artifacts that they've been cataloging. In general, we can think of ceramics as falling into a set of these larger ware types. These are general classes of pottery that have similar stylistic, visual, material elements. And we can look at the distribution of different ware types at any given site on the landscape and treat it as a kind of cultural DNA. So we can look at the proportion of different ware types recovered at any given time, and we can see how that changes over time and across space. And so this tells us something at a very high level about the culture of the people who used and discarded those artifacts. It tells us something about their artistic styles, their traditions, their access to raw material sources, and their role in larger networks of exchange, trade, and interaction. So what I did here is I took this database of 7.5 million artifacts, and I tried to find a quantitative method to estimate the flow of information between different sites on the landscape. And this is a way to reconstruct the social network in the past so that we can compare it to these large-scale climate changes. So what I did is I divided the landscape into 10-kilometer grid cells, and I aggregated together all the pottery found at every site within a single grid cell. So imagine we're just lumping together big piles of pottery across the landscape. And so then I can calculate the information content in that pile of pottery. And this is actual information we're measuring in bits here. It's using a concept called Shannon entropy. And it's basically looking at how unusual is a given distribution of ceramics that we find at a site compared to the larger average. So you can think of it as a measure of surprise. So if you find every single pottery type in equal amounts, no difference from the larger scale regional averages, there's very little information in that. You wouldn't be surprised by that. On the other hand, if you were to go to a site and find only 2 very rare types and nothing else, that would be very surprising to you. And so there's a lot of information in that knowledge. So we can quantitatively measure the information content in any one of these piles of ceramics. And then we can compare more than one pile and do these pairwise comparisons and look at the similarity in the ceramic assemblages based on this information concept and estimate the information flow. The math looks complicated here, but basically what it's saying is that we're looking at the information in site I, the information in site J, and comparing it to the average of the information in both sites, so the pile of all the ceramics together. And so again, this looks complicated, but it has a really great concrete interpretation. So if I were to, without showing you, pick one ceramic at a time from one of these piles without telling you which one it was, this measure is telling you how many sherds you would have to see before you were able to figure out which pile it's coming from. Then again, that is, so if the sites are very similar, they have very similar ceramic assemblages, it would take a lot of pottery sherds for you to figure out which one I'm drawing them from. But if they're very different, it would take only maybe 1 or 2 ceramics till you see a type that you knew only came from a certain site. So this is how we're measuring this idea of information flow. And so we can put that all together with our ceramic data and map that out in space to get an archaeological interaction network. So again, this is an attempt to reconstruct the intangible social network by looking at tangible artifact remains. And so this is what that looks like. I swear it looks better on my own computer. But we're mapping out here the intensity of social interaction. So these lighter edges look at sites that are more culturally similar. So that tells us that there was greater social interaction or contact in the past. And the darker edges are less strong ties. And so we can immediately see when we plot this out for these 50-year time steps that this is something that's changing over time. Our initial time step, we have these tight regional clusters. You can see the Hohokam here. This is Zuni, the remains of Chaco Canyon up in the north. So they're these tight, distance-based clusters. And then about the same thing in 1250. The Great Drought happens around 1275. And you can see during this period of massive migration and social reorganization that the network breaks down. These ties aren't nearly as strong, and there's not nearly as much of this rich structure that we saw before. But then, 50 years later, we can see a new network beginning to form around a new social system focused in the south, and we can see that forming and then strengthening here in our final time step. So it's clear that there is something going on here, definitely in some way related to the drought that's happening in this time period, but these dynamics are much more complicated than just a one-to-one relationship. So then we're returning to the statistical question to analyze these data, which is what are the costs and the benefits of social interaction? And particularly want to focus on the idea that large-scale patterns of drought variability in some way provide a benefit to social interaction. And this is a very common idea in archaeology. It's been discussed for decades. And it's the idea that if you're a small-scale subsistence farmer who's subject to year-to-year variability, you want to maintain social ties with people living in an environment that don't experience droughts or floods at the same time you do. So this idea of environmental correlation or anti-correlation is important for understanding, for forecasting the strength of social ties. So what's limited some of these studies in the past, though, is just the availability of data. So what I'm doing today is revisiting these long-standing questions with updated modern data sets on a much larger regional scale, and to see if we can see this image that these large-scale drought patterns are in some way shaping the costs and benefits of interaction. And so I do that, again, looks better on my computer. We can do that with this observational data set of modern-day droughts and floods from the western US, and we use this index called the Standardized Precipitation Evapotranspiration Index. And this is basically the normalized climatic water balance at a given point in space. So it looks at the balance of water entering the system through precipitation and leaving through evapotranspiration. You can think of this like a normal distribution. So an extreme drought is 3 standard deviations below the average value for a given point in space. An extreme wet period is 3 standard deviations above the norm. And so immediately, you could see, the colors were better, you could see there's quite a bit of spatial structure to the droughts and floods from year to year. And there's a lot of complexity, but there's also a lot of covariability. You can see a lot of points in space that tend to be drier than average or wetter than average at the same time. So I wanted to break down this complex variability into something a little bit more manageable. So I used principal components analysis. I'm sure many of you are familiar with how this works for mapping droughts, but I'll just go over it briefly here. So we take the time series at every single pixel in our data set. So we can look at the drought and flood patterns over time at every location in space. And we can look for correlations between those pixels and extract a set of latent time series that maximally represent the variability in this map. And so doing that, we get 6 principal components that together explain 83% of the observed drought variability over the last 100 years. So these are in units of SPE here. So positive means wet, negative means dry. And so these are these large-scale temporal patterns that are really driving this underlying variability. And we can call these principal components, or we can also think of them as amplitudes. So it's the intensity of different kinds of droughts over time. And then we can take these amplitudes and map them back on into space with empirical orthogonal functions. So these maps are representing the degree to which the time series at a given pixel correlates with each one of those principal components. And so this allows us to map out different classes of droughts in the Southwest. And so immediately what you can see here is that different drought patterns reflect different zones of moisture transport. So on the left here, we have tropical Pacific influence. You can see maritime Pacific influence. These are more continental influences. here's moisture coming from the Gulf of Mexico. And then here, it's very hard to see here, but this is the Colorado Plateau. So these are air masses that are originating in the Colorado Plateau and then reprecipitating. And so the idea is that for whatever reason in the global climate system, there's some kind of variability. So say in the tropical Pacific, something weird's going on with El Nino. This is how a tropical Pacific drought gets expressed in the southwest US. And then at any given time, a given drought is going to be some combination of these larger scale patterns. So I calculated these drought patterns on a modern day observational data set, but if you do the same thing on tree ring based reconstructions for the past 1,000 years, the same 6 patterns show up. It's pretty robust. So we know that we're not necessarily getting a signal that's reflecting modern day climate change, but these are general features of spatial variability in the Southwest. Then we can take these reconstructions and look at the amplitudes, the time series, back in time during the period of interest. So that's what we see here from 1200 to 1450. Again, our 0 line, higher is wetter, negative values are drier, and I've marked in red here the approximate onset of this great drought at around 1275. So we can immediately see that this drought was expressed in more than one principal component. So we see PC2 and PC3, those are EOF2 and EOF3, are very dry throughout this period. You have greater instability, but still dryness in PC1 and EOF1. So this is a widespread drought that's being influenced by multiple different spatial processes. Interesting enough for me, too, as you can see in PC1, after this period of the Great Drought, there's an increasing wetness and flooding. And sure enough, if you go into the area where the Hohokam were building their canals in this time period, you can see evidences that the canals were becoming increasingly washed out by flooding in this time period. So this helps to give us some confidence that these reconstructions are accurate and getting at what actually happened. So now that we've found some way to kind of quantify these spatial patterns, we can use them to infer the potential benefits of social interaction. We have to turn to the costs. So how can we model those costs and benefits statistically? So I use a tool called a spatial interaction model. This is pretty common in geography, especially economic geography. If you're studying networks of cities on a landscape or looking at how something like a border tariff will affect the flow of goods, you use a model just like this. You probably have heard them before. It's called gravity models, which is the basic type where you can estimate the intensity of interaction between two cities by the product of their sizes and the distance between them. We can generalize this idea into just thinking about 3 different causes of variability in a spatial network. So these are the origin effects. So they're the push effects that make a location more likely to interact with others. They're the destination effects, the pull processes that make a location more likely to be a target of interaction. And then there's some pairwise measurement that's the cost of interacting, which is almost always distance or some transformation of distance. So we can model this statistically. So this is the divergence, the information theory measure we calculated before. So this is the flow of information between site I and j at time t. This is a function that normalizes the data. And then we can model it as varying as some unknown function of the distance between a pair of sites. And then we can treat these origin destination effects as nuisance parameters that we're not interested in. So we want to focus on how does distance impact the intensity of social interaction. So first of all, then you have to calculate the distance between all the sites in our database. And we do this using something called Tobler's hiking function, which basically translates slope into walking speed, potential walking speed. And this is saying that an average hiker in a wildland terrain, so without a trail to use, will walk slightly faster on gentle downhill slopes. But in general, as slopes get too high in either direction, their walking speed will slow down. We can use this function in a digital elevation model of our study area to estimate the potential walking speed that a hiker would be able to attain traveling across the landscape. And then we can use these to estimate the least amount of time it would take a hiker to travel between every pair of sites in the database. So we do that, and we can use our regression function to estimate this unknown function of distance. So how does distance impact social interaction? We see that it's a nonlinear decay with distance. So within about 10 hours, it's almost a plateau. So if you can go out and talk with somebody and come back within a day's time, distance doesn't really impact how frequently you do that. Beyond a day's walk, you have this exponential decay in the intensity of social interaction. And then beyond about 100 hours, we have this long tail. And this is really exciting for me because this is entirely estimated from the data. I didn't do anything with this, but this is exactly what you'd expect from theory. If you went to the physics of moving across the landscape, this is exactly what you'd expect. So we've estimated how distance is acting as a cost for social interaction. So now we can revisit our model and add in our empirical orthogonal functions as potentially modeling the benefits of social interaction. Again, so it's more difficult to interact with sites that are further away from you, but if they experience a different drought pattern than you, you're more likely to interact with them. Their benefit is enough to make you move further distances in order to interact. So we can refit this model looking at that. And this is the result. So we fit the model for each time period separately and for each one of our empirical orthogonal functions. And what immediately jumps out to us is that there's this relationship, a positive relationship. So the less similar two sites are with respect to a drought pattern, the more similar they are culturally. But that the intensity of this relationship and which drought patterns actually matter changes over time. So in our initial time step, when we have a lot of this fine clustered structure, EOF 1, 4, and 5 are the most important. So these are the tropical and maritime Pacific signals and the continental Great Plains pattern. But during this drought period, during this period of transformation and travel, the drought patterns have no impact on the structure of the social networks. And then once the system begins re-solidifying and reforming around a new state, we see new patterns begin to emerge as being important. So what is this telling us? This is telling us that this infrastructure, these social networks are dynamic things that are adapting and responding to environmental variability. So the obvious point you might think of is the reason why these are changing over time is because the intensity of these droughts are changing over time. So in our first time step, EOF 1 is important because maybe there was a big drought in EOF 1. There was a high amplitude at that time. Turns out that's not the case. At these time and spatial scales, there's no clear one-to-one relationship between whether a drought was strongly expressed in a given time period and whether its spatial structure is having an influence on this network formation. So that could just be a case that the time scales that we need to look at are smaller. So rather than 50-year time steps, maybe 10-year drought averages might be more important. But the broader point it makes is that these processes, that we have to think of the network as a dynamic, adaptive thing that is responding and changing in response to environmental variability, but it's not strictly determined by it. And most critically is that it appears to be just the spatial patterns, not the temporal patterns, that are playing an important role here. So just to summarize what we've talked about so far, first is that 6 factors explain 83% of observed drought variability. Next, drought patterns reflect zones of distinct moisture transport. The intensity of social interaction decays non-linearly with distance. Drought patterns explain a moderate but clear proportion of social interaction, but drought amplitudes don't explain changes in the intensity of social interaction. So after talking about this, I want to briefly touch on what I'm doing now. How do we address that last question of why aren't the amplitudes, why isn't the intensity of a drought at any given time period apparently affecting social interaction? And the way I'm addressing this is using a dynamic spatial interaction model. So we already looked at a statistical spatial interaction model. It turns out that without much tweaking, we can use these mathematical models as tools to simulate possible settlement systems. Again, this is something that economic geographers do. You can put a pretty simple model, tweak some parameters, and you can evolve different settlement patterns from nothing. So we can start this simulation with a bunch of settlements with 20 people in them. Those are these small dots. And we can allow it to organically evolve over time. And we can see that we get a lot of interesting self-organized patterns from it. So we can use these as a simulation tool to understand how these systems are adapting in real time. So I'm taking these kinds of mathematical models and basically subjecting them to different kinds of environmental variability. So for example, we can have some kind of resource in the landscape and look at different degrees of spatial autocorrelation or clustering in that resource across the landscape. Or we can look at different temporal shocks of different frequencies. So what's the difference of a low frequency shock versus a high frequency variability in affecting these long-term settlement structures? And finally, we can look at the problems that we addressed today. What about large-scale spatial patterns of climate? And then what happens when we put this all together? What if you have a spatially structured landscape with a low frequency oscillation? So we can look at these general classes of environmental variability and ask how will a generic settlement system evolve over time. And by doing that, you run simulations like this. So this is, again, just randomly generated landscape, randomly seeded with settlements, and we can see that it evolves this quite complex spatial structure. And then the joy of doing simulation modeling is that we have all the data right there. So we can go from these dots on a map approach to this, and we can look at the latent networks of exchange and interaction, the flows of energy and information in this system that are underlying those dynamics. So we can use this simulation approach to learn more about our real-world case studies and ask why does the statistics not exactly match when they should. So bringing it back to where we started again, the big takeaway from this research is that we can't think of infrastructure as a static thing. Infrastructure is what makes our social systems work, and they will actively change and degrade over time if we don't monitor them and maintain them. So it's true, as we hear all the time in politics, that our physical hard infrastructure is decaying. We need to maintain that. But we also have to think about social infrastructure. So the norms, institutions, and rules are social networks that facilitate information flows in our society. They can be as, if not more important for understanding a society's resilience than hard infrastructure. And then zooming out once more, we can think about the lesson that we started this with, how to get from point A to point B, and remembering that there's not just this one-to-one relationship between drought and social change. It's easy enough to say that this point in space is going to get drier in the future, but you also have to tie this into broader global climate patterns. What kinds of droughts are you expecting to get in the future? For in Tucson, we could have droughts influenced by the tropical Pacific, the Gulf of Mexico, or more complex interactions between them. And so it's not enough to just think about dry or wet periods at a given point in space. We always have to think about the larger global and regional context of climate and climate change. Thanks for your attention.